Okay, today's video is going to be everything that you want to know about global positioning systems and in general GPS, which we're going to be focusing mostly on the United States version of satellite navigation. And that's what normally when people talk about global positioning systems, they think about the US version of GPS. There are other versions out there from the Europeans or Russians, for example, but the United States one is considered pretty much the standard, and it's open and available for people to use. It's actually a pretty amazing and significant advancement in navigation and positioning technology that has been building off of past navigation systems, which have used stars to navigate, for example, at sea. But now we've kind of, in a way, created artificial network of artificial stars, stars in the sense of navigations, to provide us global positioning all across the entire world. GPS provides geolocation in the form of longitude, latitude, and also time information to a GPS receiver anywhere in the world. So if you have an unobstructed view of GPS satellites, if you have 4 or more GPS satellites, your receiver will be able to calculate where you are and be able to even tell you what time it is. When you think about it, it's just an amazing tool that has been used in so many different applications. Look at this GPS receiver circa 1981. This is from the Jet Propulsion Laboratory, where they're making a GPS receiver in 1981. And look how large it is and requires a truck. It requires air conditioning, computing systems within the trailer that's running off of a generator, and it has that huge receiver satellite in the trailer on the back. And this is all was like needed in order to make a GPS reading. But whenever you move to today, it's just amazing to think that all the same stuff that was in this codeless receiver also is in this much smaller thing. So we've really shrunken the technology down through advancements in computer processing. So you have here a receiver antenna, just like you have in the trailer. That antenna is going to be located behind the faceplate here at the top of the GPS receiver. You have your power source, which in this case can be batteries, and then you have your head-up display, and then of course you have a central processing unit and memory storage, all built into a micro computing system within the receiver. This shrinking of GPS down to these handheld devices have really popularized, made it more accessible GPS technology, to where we use it at things like hiking or camping, or even in your car for navigation, and to the point to now even your cell phone all has GPS antennas in it. And so you can actually not just use location services whenever you have access to cellular towers or Wi-Fi, but you can also use location services when you have no signal, because you always have a GPS signal no matter where you are in the world. One thing that you should try, I've done this on a plane before. I have my phone in airplane mode, and I put the phone, I open up the Maps application, and then put the phone up next to the window of the plane, and you'll get a signal from GPS from that, and your phone will tell you where you are based off of it. It's a passive system. It's pretty amazing when you think about it, but that signal is available to you everywhere, even whenever you don't have any of your cellular antennas on. So it's actually pretty useful if you are planning on going somewhere that your phones have a GPS receiver in it as well. So the way GPS works is that there's a constellation of 31 satellites that are ready to calculate your position. These satellites orbit around the Earth in 6 orbital planes, and each orbital plane will have multiple satellites in it to ensure that there is full coverage of the planet. And so no matter where you are on the Earth, you have anywhere between, like, let's say 8 to 10 7 satellites above head at all times. Do you need to have that many satellites above you at 10 satellites at all times? That's the redundancy factor that's being added in there. So you need, like I was saying at the beginning, you need at least 4 satellites in order to calculate your position. And here, what you see is that you have a lot of extra satellites. This takes into account some cases where you might have not 100% visible sky. So you might have something like mountains in the range, or cityscapes, or buildings, or all these different aspects that could be in the range. So you really only have as much satellites that you can view the sky. So the more sky you can view, the more satellites you have available to calculate your position. So how do these satellites calculate your position? So that's the question that we want to ask. And to understand how they calculate it, it's kind of good to get an idea of how this would be done in 2D space before we start jumping to 3D space. And it's all just based off of basic triangulation. So here we have an example of the state of Colorado, and I want to be able to make a ground positioning system for anywhere in Colorado. So how are we going to do this? We're going to have transmitters that are going to transmit where they are. So for example, we can put a transmitter here in Grand Junction, a transmitter here in Fort Collins, and a transmitter in Pueblo. And so these transmitters will transmit where they are, and give us some kind of reading, giving us some kind of reading to maybe how far we are away from each one of these transmitters. And so, for example, let's start at Grand Junction. If Grand Junction sends a signal to our ground-based GPS system, what kind of signal are we going to be sending? Well, so we can broadcast in a microwave signal, same kind of signals that we could be thinking about our cell phones are using. And those signals can travel from the transmitter to the receiver. And so what we can do is that we put time into the signal, and we say, okay, what time is it at the Grand Junction transmitter when the signal leaves? And then whenever the signal arrives to the receiver, we can take those that time difference, and then we can use the fact that the microwave travels at the speed of light in order to calculate the distance that our receiver is away from Grand Junction. But for us to be able to do this, we have to have completely synchronized clocks, because we're talking about extreme speeds, the maximum speed of the universe, the speed of light. And so we have to be able to measure fractions and fractions and fractions of seconds and use that to calculate distance. And so any kind of variation in clocks at all has a major problem. So we need to have pretty much atomic grade clocks, so atomic clocks. And so if we do have this where we have atomic time on both the receiver and the signal at Grand Junction, then we just take the two times and we subtract them by each other. So we say, okay, that was the time when the signal left Grand Junction. Here's the time that the signal arrives. We subtract those two, we get some time difference and fractions of seconds, and then we multiply that by the speed of light, and then we're going to be able to get the distance of how far we are away from Grand Junction. So this all really works if we can tell how far we are from each transmitter. So that's what we're going to get off of this. And so let's say the first measurement we do, when we do the calculation, and we find out we're 250 miles away from Grand Junction. So we draw a radii of 250 miles, a circle with a radius of 250 miles. And we can see that in order for that to be true, we have to be anywhere within that blue circle. What's cool is that when we start compounding this with extra information, say we get information from Fort Collins on a second transmitter, and we find out that we're much closer, let's say in a 25-mile radius of Fort Collins. Whenever we go and map out those two possibilities, we have to be 25 miles away from Fort Collins and 250 miles away from Grand Junction. Those only gives us two different places on the surface of Earth that we can be where those two circles intersect. And so then we have idea we're either in the top part or the lower part of these two different intersections. But whenever we add a third transmitter in Pueblo, and that gives us our third circle, then we can say, okay, to satisfy all three conditions of being 250 miles away from Grand Junction, 25 miles away from Fort Collins, and 100 miles away from Pueblo, that means we have to be only at this one single spot. So if we have 3 different transmitters, we'd be able to do what we call triangulation, just basic triangulation, to find out where we are in the world. So all this only really works if our GPS receiver can know where all the transmitters are. So we have to know exactly where Pueblo is, or where Fort Collins or Grand Junction is, exactly where the transmitters are. In GPS, we can do this by having our GPS signal also transmit the satellite location. So in GPS, actually our signal has an almanac of where all the other satellites are. So whenever you find out that you're getting a signal from satellite number 2, for example, satellite number 3 or 4, whatever satellite you would have had before, would have told you where where to expect satellite number 2 to be at. Everyone has to have perfect clocks. So this is kind of a problem. So in space, the satellites have atomic clocks built in on them. So they have perfect time going on over there, and they do some calibration also to take into account Einstein's rules when it comes to travel at fast speeds and its relativity in time. So they have all this calibration happening on the clocks in space. So the clocks in space give us atomic time for that satellite. But the problem is that atomic clocks are really big and require a lot of perfect maintenance and energy and so forth. It's something that you don't carry around in a pocket. And so in GPS, what we do is that we use 3 satellites to calculate our position, but we use the 4th signal to make our clock on our receiver. So the fourth signal actually serves as a receiver, and so that's why you need 4 satellites. And so we're gonna see in a second, though, when you're talking about 3D space, you're gonna say, well, don't you need actually 5 satellites? Well, I'll explain why you only need 4 in a second. And then you have to be able to tell all the transmitters perfectly apart. So you have to have some kind of code name for each transmitter. And so in GPS, we have each satellite's having an identification number, and that's transmitted with the signal. So you know exactly which one it's coming from. But then also the big problem that we have in GPS is that we're not dealing with longitude, latitude, locations. Just longitude, latitude. We also have elevation. We have 3 dimensions. So we live in a 3-dimensional world, and our positioning system has to be 3-dimensional as well. And so we're not going to be intersecting 3 circles. We're actually going to be intersecting 3 spheres. And so this is where it becomes kind of interesting, because whenever we take 2 satellites in space, instead of saying, we have the first satellite saying, hey, you're this far away from me, but you're that far away in 3D space, so you have to actually draw a sphere with the radii of that distance. So if it tells you, oh, okay, you are, 100 miles. Well, I guess in the case of GPS, it's more like about 12,000 miles. So, but then say the satellite says, oh, you're 12,000 miles away from me. It's going to draw a sphere of 12,000 miles that you can be anywhere within that sphere from the satellite. And so whenever you take 2 signals and you put those together, to satisfy both constraints, you're going to be anywhere within a circle of that intersection. So you can see that circle that you can be anywhere within that circle. As soon as you add 3 spheres, then you got 2 points. And so this is where it becomes kind of interesting, because in reality, to be able to get a perfect location, you need to have only 1 point. So you would need a 4th sphere, and then you can say, okay, to satisfy my distance from all 4 satellites, I can only be at this 1 point. But in GPS, there is an assumption that's made in the receivers, is that you're not 12,000 miles below the surface of the Earth, or 12,000 miles above the surface of the Earth. They make an assumption that you are within the biosphere. And so that's one thing that's kind of interesting in the receivers, is that one of the points that's going to show up in either deep space or the center of the Earth is going to be eliminated. And so it's going to actually end up using only the other point to say that's where you are. This is why you can use only 4 satellites, because the 4 satellites can be used for time. The truth is, the best GPS readings or I guess it doesn't matter, because logically you're using this. but the best GPS readings would have 5 satellites, 1 that's used for time and then 4 that you would use for position. But in this case, you can actually get away with just 3 for position because of this assumption that you are on Earth. So what would happen if you took that GPS satellite into deep space? Well, you're going to have to rewrite the GPS receiver into deep space. You're going to have to rewrite the GPS receiver's programming to be able to say that it needs more than 3 satellites, that it needs 4 satellites in order to get good readings. But you'd also need a whole different coordinate system that it's working off of, because it's still trying to get you longitude, latitude, projections. So you'd have to have some kind of 3-dimensional coordinate system for space. But anyways, I'm digressing. So one thing that's very interesting about GPS units is that they do not transmit signals to the satellites. So GPS units are passive receivers. They just sit there and receive information from the satellites. So we actually don't know how many people are using GPS or when they're using it or who's using it. And so that's actually a pretty amazing thing, especially whenever you think about that this is developed by the United States military and given as almost as a public service for the world. It's kind of interesting to know that something is being used completely anonymously. And so what GPS does, it just measures differences in distance between all the different satellites that are available to it. And then whenever it measures those differences in distances, it puts that together and tells you what location you are in. So here's our GPS unit. It sees 1 satellite. It draws out that sphere and knows that it's somewhere within that sphere. Then it gets 2 satellites. That draws out 2 spheres. And we end up with that circle that's going to tell us where we're located. Anywhere within that circle, that's the place where the 2 spheres intersect. Once we get 3 satellites, that's where we have the 2 points. And so we know that one of those 2 points is going to be the surface of the Earth, and so we know where we are. But the truth is, once we get the 4th satellite, we're for sure where we are, even with elevation and everything, because we have all 4 satellites. And so and just remember that whatever satellites your receiver is telling you, you have 1 is being used for time. So in this case, to have 4 location satellites, you have to have a 5th satellite for time. And so GPS accuracy. So how accurate is it? So most GPS units using the 24 satellites that are up in space, and that includes, the reason why I said 31 before, because some of those are backup satellites. So they have 24 satellites hanging out over there. If you're using just the GPS satellites out there, you're going to have about 15 meters of error, somewhere in that range. 15 meters is not, when you think about it, for surveying, is not that great. For navigation, it's pretty good within 15 meters. Whenever you start looking at other satellites, whenever you start talking about augmenting your GPS, not just having the 24 satellites, but also adding in ground stations, you can increase that accuracy to less than 3 meters. This augmentation is called Wide Area Augmentation System, and that system is put in North America, and also in the parts of Mexico and Canada have already added those in as well. And basically, this has been set up because the Federal Aviation Administration, FAA, doesn't think 15 meters is good enough for navigation when it comes to airplanes. They want to have much better navigation. So having the WASP system in play over North America gives the navigation systems in planes up to 3 meters. What's nice though is that if you have the receiver, the WASP receiver on your GPS receiver, you can use both systems, the GPS systems and the ground-based systems, and actually get less than 3 meter accuracy on your GPS receiver. When we talk about 3 meters, that's very good accuracy for what people want to do. And so you can see here the WASP system that's available. This is a little bit older graphics, so some of these ones that say new WASP systems are already up and running. But you can see here, Alaska, parts of Canada, and Mexico have been added in. And so now with that, we're going to have much higher accuracy. The truth is, if you are even in parts of Central America, if you point your receivers up towards Mexico areas, like just point it north while you're taking your signals, you could probably get some WASP readings as well, and which is going to get you that 3-meter accuracy. So that's something to consider whenever you're in anywhere within North America. But if you're inside the United States or Mexico or Canada, you're going to be able to get pretty good readings no matter where you are, and they're going to make a big difference for you. And so let's talk about going further than just recreational grade. So, the normal GPS receivers that you get for hiking and kind of stuff, we're going to say they're accurate within 5 meters. That's because you're using that WASP system. They're pretty cheap, let's say within $100 to $800. Depends if you start adding different kinds of features, color, cameras on them, how much they can store, do they have a lithium battery. This kind of stuff is where the prices come in. But the underlying technology within all the GPS units is exactly the same, and they're all going to have the same accuracy. So sometimes they're going to try to tell you, oh, if you get this external antenna, or if you get this kind of like ours is better at receiving signals. A lot of that's just them trying to sell you on stuff. So that's not always necessarily true. Only reason why I say I like the external antennas that come on GPS receivers is because that you actually see it. So then you don't block it yourself with your own body. The next grade is going to be the mapping grade GPS. And this works whenever you have 2 units. You take 1 unit and use it as a base station, and then you have your other unit as you go around and you do measurements. That one that's a base station just sits there and reads the noise from the signal, and then afterwards you do differential correction with differential processing software back in the office, and then you get that up to less than a meter accuracy. What's interesting about mapping grade GPS and recreational grade GPS is that the technology underneath it is not, and there's no difference. Again, you're using the same kinds of antennas, same kind of units, all this other kinds of stuff. And what you're going to see is that normally in the recreational grade, you're going to hear about Garmin, and you're going to hear about things like Garmin. Basically, Garmin is the big one out there, but there's also some smaller brands called Magellan that's out there as well. But and then when you get to mapping grade, you're going to hear about Trimble. And so there's kind of like don't step on my market kind of thing, where Trimble is doing the mapping grade, but they're not making recreational grade stuff, and Garmin's doing recreational grade and not making mapping grade. The only difference between the two different products is that the Trimbles are going to store the raw signals as they're coming from the satellite. So the satellite, receiver receives the signal, it records the whole signal, and then later on you can post-process it, while the recreational grade's not recording that signal. So recreational grade is just processing the signal and recording your position. So if you're just recording the position, you can never post-process. But with mapping grade, since you record the whole signal, you can actually go afterwards and say, okay, I was getting these 3 or 4 or 5 satellites, and this was the information I was getting at this time, and now I can use my ground-based station to tell me what the noise was from each one of those satellites, and then post-process it to get that 1 meters. So basically, because that signal is being stored on the device, that's what makes it a mapping grade, because you can store it on the device and then differentially process it later. But then again, you're still only getting 1 meter accuracy, which is great for mapping, but it's not great for surveying. Surveying, you want to be within a centimeter. This is what you're going to be looking at for designing, making buildings and bridges and this kind of stuff. You want to be as accurate as possible. These units are very expensive, $15,000 to $30,000 in survey grade, but they also come with annual contracts where you have to pay for some kind of subscription service to get augmented systems. So basically, the way survey grade GPS is working is that they're providing additional ground-based stations that you subscribe to, and those ground-based stations are augmenting on top of GPS and on top of WASP and everything, to where you get that accuracy within 1 centimeter. And so those are usually They say only really for professional grade. So if someone asks you to go do a land survey, map out my property lines, for example, doing that with a mapping grade GPS would get you within 1 meter, which a lot of times that's not good enough for mapping out property lines. So I would say that it's probably at that point you're going to have to get yourself a professional surveyor, because they're going to have access to the high grade positioning systems. So what does the Garmin recreational GPS kind of look like? This is the older version of eTrex, but they all been basically the same. They have this kind of pages system where you have different pages that show up on the LCD screen, up and down, to go through the different pages. They usually have a backlight that you're going to want it to turn off after a while to conserve your batteries. And then you'll have some kind of stick for navigation. Normally I like working off the heads-up display like this because it gives you an idea of how many satellites are above. So you can see here in this diagram, we have 1, 2, 3, 4, 5, 6, 7, 8 satellites. Everything that has a black dot is a satellite that you're connected to. The ones with the white dots, they're there because you know about them from the almanac that's downloading, but you're not getting a signal from them. So maybe something's blocking you, for example, from your west and your south side from seeing that part of the sky that would have the satellite. The further away from the center, the closer to the horizon it is. And then you can see here the signal strength from each individual satellites on the bar chart. And then, of course, the location being read off here in degrees and decimal minutes. And then, of course, you have your elevation there in feet. And so whenever you start going through the GPS unit, of course you want to turn it on. But after you turn it on, if you use the power button, that will make the screen bright again. This can be useful because then you can turn on and off the brightness by just pressing the power button. But if you hold the power button, that's going to actually turn on and off the units themselves. And you can see here it gives you kind of a reading about how accurate it is. Most GPS units are going to try to tell you kind of an accuracy reading on the screen just based off of signal noises. But you can see here again the heads-up display. I like using the heads-up display because it just gives me an idea of how the system's working. There's always these other features here like mapping waypoints, which are going to be places that you're going to maybe hike to. This kind of stuff is really great for kind of geocaching or trying to go on hikes, for example. But when it comes to doing kind of surveying kind of GPS work, or let's say just making some points for maps and stuff like that, normally what you want to do is you want to record longitude, latitude, locations, and so you can store those as waypoints into your unit, and then later on download those with the cord that you plug into your computer and so forth. But honestly, I never trust those, and I don't think you should ever trust those either. And so what I've been telling people to do is to take a camera with them, and you just take a quick shot, a picture of your screen of your GPS as you're trying to record points. Go ahead and store them as waypoints as you want, but don't rely on that. Either take a picture of it or write it down. That's another thing. You can just actually literally just write it down. One thing though to be careful about if you do go on the camera route of taking pictures is you have to be careful about interference from your cell phone. So your cell phone actually, the signal from it will be quite strong, and if you put it too close to the GPS unit, it will end up giving you bad readings because it will interfere with the GPS's microwaves in your cell phone. So just keep your cell phone on airplane mode if you want to take pictures really close, or just try to keep them far apart from each other, or use a normal point and shoot camera. If you press the buttons, you can go to the satellite page, and normally that's where I like to keep it. Remember that you need to have 4 black bars on your satellites in order to say that you have a proper signal. That's what you need to be looking out for on a GPS unit. Also, this is going to be the best way to hold your GPS. You're going to want to keep it somewhere near, further away from your body. Don't keep it too close to your body. You are blocking the sky as well. Trees don't really block the sky, foliage kind of stuff. So you could be in thick canopy forest and still get GPS signal, but things like buildings will block the sky. Your body will block the sky. So keep that in mind. And then also remember, stay away from other microwave devices. So you might want to keep that phone in airplane mode, or turned off in order to have to keep your GPS unit working great. And so just a quick note is that, remember, you need to have 4 bars in order to get your reading. Also on the settings, you want to keep that in WGS 1984, World Geodetic System 1984, and that's going to be the native datum for GPS. I like taking my readings in degrees, minutes, decimal seconds. That's going to give you the most accuracy. Stay away from the decimal degrees, as that will be an option for you as well. Well, thank you for paying attention and learning all that you can about GPS. I hope you have a fun time